Tomorrow is the kind of calendar date that science writers and late-night talk show monologists both circle for different reasons. For the astronomer, October 29th, 2025 is a tidy mark on an ephemeris, perihelion, the closest approach of a newly famous interstellar object to our sun. For everyone else, it reads like a line in a thriller. The moment of truth, the decisive test, the night we find out if the universe is more stranger than we imagined. Either way, the same uncomfortable, irresistible question hums under everything. What will Atlas do when the sun turns up the heat? Atlas isn't a name born of affection so much as shorthand. The third interstellar visitor cataloged in our modern records, following the odd, elongated speck that shocked telescope operators a few years ago, and the more conventional interstellar comet that behaved like the comets we thought we understood. This one arrived with a set of numbers and behaviors that refused to fit tidy categories. And when a set of numbers refuses to be tidy, the work of science is to stare right at the mess until it starts to make sense. The public, meanwhile, prefers stories, and Atlas has handed them a very good one. Here are the facts that set the stage, as carefully as we can state them without claiming certainties the data won't yet support. Atlas will skim past the sun at roughly 203 million kilometers, about 1.4 astronomical units, a path that threads it somewhere just inside the orbit of Mars. At perihelion, it will receive roughly 770 watts of energy per square meter from the sun, the same kind of intense baking a typical comet experiences on its inward swing. In space, without an atmosphere or oceans to mellow things out, heat doesn't melt. It drives sublimation. Solid to gas, instant. For a normal comet, that process produces the glowing halo and the trailing fan of dust we see from Earth. The coma and the tail. Because volatile ices vaporize and carry dust with them. If Atlas is a garden variety comet, a fragile agglomeration held together by weak forces, this sunlit oven could be catastrophic. Those weak bonds can't hold when the thermal stresses and internal gas pressures spike. The object can fragment into a shower of smaller pieces that vaporize quickly because smaller bodies have more surface area per unit mass. The night sky could erupt, in astronomers' terms, into a spectacular brightening, a plume of gas and dust that telescopes and cameras would feast upon for weeks. If, instead, Atlas is not a natural ice ball but something else entirely. Technology, or at least engineered structure. The outcome could look very different. What if the heat triggers behavior rather than disintegration? What if the object maneuvers, or expels smaller devices, or shows signatures that no natural process produces? Steady artificial lights, concentrated thermal emissions like an engine, or directed ejections inconsistent with sublimation physics? That is the hypothesis Avi Loeb and a handful of other researchers have pressed as a possibility worth taking seriously, not because it is fashionable, but because the anomalies in Atlas's observed behavior compel a sober accounting. The anomalies begin with the object's motion and geometry. When Atlas was first cataloged by the Asteroid Terrestrial Impact Last Alert System on the night of July 1st, it looked, for all intents and purposes, like a moving point of light, another object in the sky. Timing its motion revealed something striking. At the distances it was measured, it was moving faster than anything we've tracked within the solar system. Measured velocity clocked in around 58 kilometers per second. To put that in human terms, Earth races around the sun at about 30 kilometers per second. Mercury must maintain close to 48 kilometers just to avoid falling into the sun's gravity well. Atlas was faster than that, an unmistakable hallmark of an interstellar interloper, a hyperbolic trajectory that says plainly, it did not originate here. But speed alone isn't the only oddity. The direction of approach was a near miss from geometry's randomness. Atlas came in at just 3 degrees off the ecliptic plane, the thin, flat slice of the sky where our planets orbit. In a universe where objects can arrive from any direction, that alignment is suggestive. A comet or asteroid from outside our system could have approached from high above or below the plane without regard to where planets lie. Instead, Atlas entered almost exactly in the same plane where all our planets move. An uncanny, and some would say suspicious, coincidence. Size and composition raised more questions. Compared to the two prior interstellar visitors, Atlas was not subtle. Estimates placed its diameter potentially as big as 5.6 kilometers. Orders of magnitude larger than the elongated 400-meter object that first opened the debate about non-natural origins, and larger than the roughly 1 kilometer-second interstellar comet. Being larger is not in itself suspicious, but it increases the stakes. A larger body interacts more noticeably with planetary environments and offers more surface area for complex behavior. Then there was the chemical and polarimetric strangeness. Observations of Atlas's coma, a diffuse cloud surrounding it, showed it forming while the object was well beyond where we typically expect comets to begin boiling off volatiles. At more than 5 astronomical units from the Sun, it was already shrouded in a coma dominated by carbon dioxide, with a far higher CO2 to water ratio than cometary templates predict. On the order of 8:1, carbon dioxide sublimates at much lower temperatures than water ice. If dry ice outside the grocery freezer is any guide, CO2 will puff into gas well before water turns to vapor. Seeing a CO2-dominated coma at that distance is a genuine surprise. Polarimetry. The study of how light is polarized when it reflects off a surface, added another flash of surprise. Most solar system objects show positive polarization properties. Atlas was strongly negatively polarized, more extreme than anything previously recorded. Negative polarization and its magnitude point toward unusual surface or structural properties, porosity, composition, geometry, perhaps a surface layer of weird grains. It's data that resists comfortable comparisons with known cometary materials. Finally, metals. Early summer spectra picked up nickel in the surrounding cloud, but little or no iron. Since nickel and iron are typically found together in planetary materials, their separation posed a chemical puzzle. What process could liberate nickel while leaving iron behind? Later observations in late September shifted that picture. Iron showed up and the nickel-to-iron ratio trended toward something more ordinary. It's tempting to draw neat conclusions. Maybe an initial release mechanism favored nickel, or maybe some optical bias skewed early readings. But right now it's an empirical fact that Atlas's chemistry evolved in an odd, almost staged way. All of these threads. Trajectory, alignment with the ecliptic, CO2 heavy coma, extreme negative polarization, odd metal ratios, conspire to make Atlas less comfortably classified than any interstellar visitor before it. And when multiple independent anomalies cluster, scientists put down their priors and listen more carefully to the data. Avi Loeb, a Harvard astrophysicist who has been unusually outspoken about the possibility of non-natural origins for interstellar objects, calls perihelion the decisive test. He's been explicit that this is a moment when natural and artificial hypotheses fork on observable consequences. There is another image, Loeb, and others who ponder the question. Keep pulling out of the drawer. The Trojan horse. The metaphor is blunt because it's evocative. The city of Troy fell because its guardians mistook a hostile payload for a harmless gift. If Atlas merely looks the part of a comet while harboring something else, a payload of microprobes, a hidden mechanism, a deliberate distribution system, then surface appearances could be designed to mislead. That possibility isn't a Hollywood script. It's a risk scenario that says, if you can't see the interior, you must be more suspicious about what exterior behavior conceals. A crucial practical limit tempers the drama. We can't watch Atlas's closest approach happen in real time. Perihelion will occur on the far side of the Sun from Earth's vantage. The luminous glare of our star blinds optical telescopes in that direction. The most dramatic action. Fragmentation, ejection, thermal emissions, maneuvering. Could be playing out behind a veil of photons we cannot parse. It is a maddening observational blind spot. And it's the kind of frustrating constraint that fuels both rigorous instrument planning and more speculative conversation. If decisive evidence of natural fragmentation arrives in subsequent months, the telltale cascade of fragments, a characteristic distribution of dust, a chemical fingerprint that fits known cometary physics. The story ends in an archetypal way. Atlas was a weird, unusually large, CO2-rich comet that surprised us but ultimately obeyed known laws. If instead instruments detect unusual thermal patterns, coherent light sources moving in non-ballistic ways, or a coordinated arrival of mini-objects, the implications would be huge and immediate. The object would be behaving like a hosted system, a carrier of secondary bodies with directed purposes. Either outcome reshapes our understanding. Either we learn how extraordinary nature can be, or we learn how extraordinary the products of technology might be when they cross interstellar distances. Beyond the science and the spectacle are the operational follow-ups already lined up. Atlas will not simply vanish after perihelion. It will cross back into regions where Earth-based and spacecraft observatories can monitor it again. Early November will bring a close approach to Venus at roughly 97 million kilometers. In mid-December, the object will be on a course that could take it within some hundreds of millions of kilometers of Earth. And by March of 2026, Atlas is scheduled to pass at a distance near Jupiter, where missions like Juno or others might have opportunity to take targeted observations or radio checks. Researchers and mission teams are preparing to watch and listen for any anomalous activity in those windows. The Galileo project, for example, has already been asked by Loeb and collaborators to keep an eye on the sky for any unusual entries or anomalous objects in Earth's atmosphere in the months following perihelion. The approach is not alarmist. It is methodical. Data collection, cross-verification across instruments, careful statistical analysis. These are the tools that corral speculation back into science. The difference between wonder and panic is the discipline to check and recheck, to publish raw data, to invite scrutiny, to be explicit about uncertainties. At its heart, the Atlas story is a reminder about how science is actually done in public view now. We live in an era when a discovery goes from detection to global conversation in days, not years. Citizen scientists tune telescopes. Amateur observers post images. Social networks amplify every rumor. The doomsayers and the sober voices both speak loudly. The right public response, and in the view of responsible scientists, is curiosity tempered by skepticism. Watch the data, read the papers, demand reproducible measurements rather than headlines that monetize fear. That admonition matters because the stakes are both intellectual and practical. If Atlas is natural, we will have learned how interstellar materials can be more variable than models allowed. If Atlas is engineered, we will have the most profound evidence to date that non-Earth intelligence has sent devices into our neighborhood. And that would raise cascading questions about detection, defense, ethics, and policy that no discipline is fully prepared to answer. Avi Loeb and colleagues have urged policymakers to take seriously even low-probability, high-impact scenarios, not out of paranoia, but out of prudence. Black swan events, by definition, surprise us, and anything that surprises us with such consequences deserves sober contingency planning. It is appropriate, then, that the calendar places the moment almost theatrically before Halloween. We are, in a way, about to unmask a cosmic stranger on the night before a holiday devoted to masks. The metaphor is irresistible, but it also has a practical lesson. In observational astronomy, masks are common. Spectra, light curves, polarimetry. These are ways we try to rip off the mask and see the internal mechanics. Perihelion is simply one of the clearest, hottest ways nature forces the mask to slip. For now, though, all we can do is wait with our instruments trained and our analytic tools ready. The immediate hours around perihelion may yield no public spectacle visible from Earth, because the sun stands between us and Atlas, but telescopes in other bands. Radio, infrared, spaceborne imagers in strategic orbits, and the patient months that follow are where answers will emerge. The data pipeline will spool out discoveries and corrections, and our task is to read them carefully. Whatever the verdict, Atlas is already doing what great discoveries always do, forcing us to re-examine what we assumed was routine, to sharpen our models, to clarify our questions, and to consider possibilities we had relegated to speculative fiction. In science, that's a good thing. The universe is not obliged to be comprehensible to us on our first pass. It is obliged only to be truthful in the data it offers. Tomorrow we will see another page of that data, even if only indirectly. In the coming months, as Atlas moves past perihelion and back into regions we can observe without the sun's blinding glare, we will have clearer answers about whether it is wearing a comet costume or something more deliberate. And if the object does remove its mask, as Loeb has phrased it, the consequences will be debated across laboratories, policy forums, and late-night panels. If it doesn't, we'll still have learned something about the kinds of materials and trajectories the cosmos can throw at us. Either way, October 29th, 2025 will stand as a date when curiosity met an object that refused to be ordinary. And that, when you strip away the metaphors, is why astronomers spend long nights watching tiny specks of light move against the dark, because those specks sometimes carry the questions that change everything.
Visitor from interstellar space. New calculations suggest the